Hello, Algebra 2 students. It is I, Mr. Kingsbury. Today I want to go over two things with you. One, we're going to talk about exponential growth and decay. Two, we're going to work a couple of logarithmic functions together. So let's start with exponential growth and decay. Right in front of you here, I have both formulas. They both have the same four basic parts. There's an initial amount, that's A. There's a growth rate, R. There's a number of time intervals, that's X, and then there's the current amount, which is Y. The only difference between these two is that growth has addition and decay has subtraction. That's the only difference. And you're going to figure out which one that you need to use based on the word problem. Now, all I'm going to ask you to do is to write the equation. I'm not going to ask you to solve it. So we're going to write a few here in just a second together. There are a couple of things I want to make sure you're aware of. First of all, the growth rate will be given to you as a percent. You will have to convert that to a decimal, and I'll remind you how to do that, but it must be a decimal in here. Otherwise, the growth will be ridiculously fast, and we don't want that. The other thing that I need to make you aware of is that this doesn't say number of years. It says number of time intervals, and we will know what a time interval is based off of the growth rate. It may say 2%, but it may be 2% per day, or 2% per month, or 2% per year, or 2% per every decade. It depends. So you have to take whatever time they've given you and adjust it so the number you're using works with the growth rate. For example, if it's 2% per month and they say 2 years, you need to convert that into months so that the number that you're putting in is months. Very important. So let's do a couple of these real quick. You're going to see that for each one, I'm going to identify whether it's growth or decay, and then I'm also going to write out what the variables are, write the equation, and then fill it in. So let's start with number one here. The first U.S. Census took place in 1790. The population was 3,929,214. The growth rate of the U.S. population was 2.03% per year. What was the U.S. population in 1800? So let me write out my A, my R, my X, and my Y. And let's see if we can fill these things in. So A, what is the initial amount? I think that would be 3,929,214. What is the rate? Looks like it's 2.03% per year. Now, how do I turn that into a decimal? You take 2.03, you locate the decimal, which is right here, and you move it 2 places to the left. Notice there's this empty spot. I'm going to put a 0 there. So I would write 0.0203. That's what I'm going to use for the rate. X is the number of time intervals. This says it's 2.03% per year. So X is going to be the number of years. Well, we're not sure how many years went by. We just know the first one was in 1790 and the second one was in 1800. So what I can do is subtract those to figure out how many years has gone by. That would be 10 years. And lastly, what's the final amount? We don't know. That's what it's asking. What was the population in 1800? So we could figure that out. Let's write an equation anyway that we could use to figure it out. So y equals A times 1 plus R to the X power. And we can start plugging stuff in. We don't know what Y is, so that stays the same. A is going to be 3,929,214. 1 plus R, my R is 0.0203, and we will raise that to the X power. X is 10. There's our equation. Do not solve it, although this one will be pretty easy. We can just type that in the calculator. Do not solve it. Not necessary. By the way, I should have identified that this was growth. I know this because it says the growth rate. Right there, growth rate. Number 2, you drink a beverage with 120 milligrams of caffeine in it. Each hour, the caffeine in your system decreases by about 12%. How much caffeine will be in your body after 8 hours? So for starters, I underline decreases because that tells me this is decay. And then I will write out A, R, X, and Y. A is the starting amount, that's 120 milligrams. The rate is 12%, which I will rewrite as a decimal. That will be 0.12. And notice that's per hour, that's each hour. So when we go to X and it says how much caffeine will be in your system in 8 hours, we already have the appropriate unit, so we can just put 8. And we don't know what Y is because it wants us to figure that out. Our equation will be Y equals A times 1 minus R to the X power. Let's plug in. We don't know what Y is. We know that A is 120. We got 1 minus R. R would be 0.12. And that's to the X power, which is 8. So there we go. 2 down, 2 to go. Let's talk about a coin collection. Gotta love that. So we have this coin collection. Currently, our coin collection is worth $4,312. If your coin collection is worth $8,000 in 5 years, what was its annual growth rate? So this is growth. Now let's figure out what A, R, X, and Y are. So A is 4,312. R, we don't know. It says, what is the growth rate, the annual growth rate? We don't know, so that's what we're going to be looking for. X would be the number of years, since it's an annual growth rate. Annual means years. It says 5 years. So we can put 5 there, and then the final value will be $8,000. Our equation is Y equals A times 1 plus R to the X. And let's plug in. My Y is 8,000. My A is 4,312 times 1 plus R. We don't know what R is, so we'll just leave it as R. And my X is 5. Just plugging in. And then one final one. I'm going to jump down a little bit to number 6. Number 6 talks about half-life. Half-life is used to do all kinds of stuff, but primarily to figure out how old things are. Present in all forms of natural rock and such are radioactive elements. Now, elements are radioactive when they have extra protons or extra electrons. I think it's just extra electrons, actually. And what happens is this. As those extra electrons get ejected off of the atom, because the atoms of these elements, they want to be stable. They want the same number of protons as electrons. So if there's extra electrons, the atoms start shooting off those electrons. That's what makes it radioactive. At some point, though, an atom will have shot off all of the extra electrons it has, and it will have the same number of protons as electrons, and it will be stable and no longer radioactive. And at that point, it has become a different element. So what scientists do is they can measure how much of the radioactive element is present in a sample and how much of the element it turns into is present, and then using the half-life, which is the rate that it decays, they can figure out how old the thing is. Now it's called half-life because it is the amount of time it takes a certain amount of radioactive element to become half that amount. Like if you had 10 grams, how long it would take it to become 5 grams. And interestingly enough, no matter how much you have, it always takes the same amount of time to become half of that. Isn't that crazy? So like if you had 80 grams of something, it would take the same amount of time from that 80 to get down to 40 that it would to go from 40 to 20 and 20 to 10 and 10 to 5. Same amount of time every single time. That's called the half-life. What you need to know is that this is decay because half-life is decay. And you need to know that if we're finding half, that the rate is 50%. Keep that in your mind. So let's figure out what A, R, X, and Y are. And as I just said, the rate, because it's half-life, is half of it, or 50%, which as a decimal is 0.50. Now we're starting with 1,500 grams. And we don't know how much will be left, so we don't know what Y is, but we know it's after 4 years. Now here's where we have an issue. It says 4 years, but the half-life is 6 months. So the rate is 50% every 6 months. So we need to take this 4 years and multiply it by 12, and that gives me 48 months. So this is years, and this is months. So we need to know in 48 months, how many times is this sample going to get cut in half? If it gets cut in half every 6 months. So I'm going to take 48 and divide it by 6. I get 8. So my x value will be 8. In 4 years, this sample will hit its half-life 8 times. Now the equation is still y equals a times 1 minus r to the x. And now we can plug in. We don't know what y is. We know that a is 1500. We got 1 minus 50%, 0.50, and that's raised to the 8th power. And you could plug that in the calculator if you really wanted to. So that's how you write exponential growth and exponential decay equations. Now I have a couple of logarithmic ones. There's actually 4. We'll do 2 now, and then we'll do 2 in a little in class. Now, you may have noticed that with the exponential growth and decay, it was a formula, and it applied to a whole bunch of different situations. There were even a couple more I didn't touch. They were all over the place. That's because the growth and decay formulas are applicable all over the place to all kinds of very different situations. Logarithms do not have a formula like that. They just have formulas that are applicable to a very specific situation, like number 7 here. Number 7 talks about the Richter scale, which is used for measuring the magnitude of an earthquake. So in a second here, we're going to use that, and we're going to actually solve this, which is why I paused for a moment. We will be solving. So hang on to your hats. So it turns out that the Richter magnitude can be found using this equation. M equals the log of I over 0.001, where M is magnitude and I is intensity. Please don't ask me how they figure out the intensity. I suspect they have some sort of device that they can use to measure the intensity, and then they use this equation to convert it to a magnitude. If an earthquake has an intensity of 5,924, what is the earthquake's magnitude? And we're going to round to 1 decimal. Not a big deal. So we'll use our equation here. M equals the log of I over 0.001. I am so sorry for my handwriting. What they do tell us is that the intensity is 5,924. Notice there's not any units. I don't know what 5,924 watts. I don't know. We'll just call it units. So this will equal the log of 5,924 over 0.001. And what's great is I can type this right into the calculator. So let me just get out my calculator here, turn it on, and you'll notice that there's a log button right off to the side here, right there. We're going to use that. Hopefully we've talked about this in class already. So I need to type in the log of 5,924 over 0.001. So I'm going to hit the log button, and then inside the parentheses I need to make a fraction. So I will hit alpha y equals enter. That gives me my fractional prompt. I will put 5924 in the top and hit the down arrow. I get 0.001. I will hit the right arrow and hit parentheses. And now all I have to do is hit enter, and I get that. Now remember, it says to round to 1 decimal. That means I need 1 decimal point after, one number after the decimal point. So I'm either going to round this 7 up to 8 or leave it at 7, depending on what's immediately next to it. If what's immediately to its right is 5 or bigger, I will round up to 8. If it's 4 or smaller, I will leave it alone. So I'm looking at this 7, and immediately next to it is another 7, which is 5 or bigger, which means I need to round this 7 up to an 8. So this will be 6.8. And again, there are no units, but there you go. One more and then we're done. So the wind speed S in miles per hour near the center of a tornado is related to the distance in miles the tornado travels by this equation here. S equals 93 times the log of D, there should be parentheses there, plus 65. On March 18th, 1925, a tornado whose wind speed was 320 miles per hour hit the Midwest. The question is, how far did the tornado travel? So let's start with the equation here. S equals 93 times the log of D plus 65. And we are told that the speed was 320. S's speed, so I can replace that with 320. So 320 equals 93 times the log of D plus 65. Now, before I can do anything with that log, I got to get all the stuff that's next to it away. So I'm going to subtract 65, no big deal. On the left, I get 255. On the right, that makes a 0 pair, and it equals 93 times the log of D. So now I need to undo times. To undo times, I use division, and what I do to one side, I do to the other. I will divide both sides by 93, and I will continue my work up over here. I need to show you something, though. If I divide 255 by 93, I get a pretty bad decimal, one that I don't like very much at all. Now, what a lot of people want to do is they'll go and they'll round this, and they'll use the rounded number. Here's the problem. When you round a number, you lose accuracy. And I know it doesn't seem like much, but if you use an inaccurate number multiple times in multiple ways, then the overall number ends up losing its accuracy, and it gets further and further off. We want to keep our stuff as accurate as possible. So here's what I'm going to write. Yes, the 93s make a 1. That's great. I'm going to leave this as 255 over 93. And that's going to equal the log of D, because 93 divided by 93 is 1, and 1 times the log of D is just the log of D. Now here's where we have fun. You'll recall the second day, I think, of class, we talked about converting. And we can convert a logarithm to an exponential. Why would I want to do that? I would want to do that because in exponential form, this D would be by itself. I'll show you. So first I need to know what the base is. If the base is not written in, it's 10. So I'm going to rewrite this. I'm going to take 10. I'm going to raise it to the 255 over 93rd power. And that will equal my D value. Now I can go to my calculator and type this in. Off to the side right here, there's a 10 to the X key. So I'm going to hit second, 10 to the X. And then I need to put in 255 over 93. So I need a fractional prompt for that. So I go alpha y equals enter. Now I have my fraction. 250 on top. 93 on the bottom. Arrow out. Enter. And I get this long number. And it doesn't tell me how to round. So I'm just going to go to 2 decimal places, which means I'm either going to round this 9 up or leave it alone. Immediately to its left is a 5. That means I need to round this 9 up. Well, when you round 9 up, you round it up to 10. So I would put a 0, but I'd have to carry the 1, and then you get 9 plus 1, which is another 10. So I'll put that 0, and then I need to put the 1 over the 1, and that becomes 2. So this becomes 552.00 equals D. No big deal. Thought I'd share that with you. We'll do the remaining ones in class. Thanks for hanging with me, and I will see you later.